Good morning, afternoon, and evening, everyone. I'm Rob Meyer. I run outbound product management here at GridGain, and I will be your host today for today's webinar around database durability and best practices for native persistence and data recovery with Ignite. Before we get started, I just want to make sure to do a bit of housekeeping to make sure you know your way around the application and you know how to contact us, either if you're having problems or if you have questions. So if you look at the upper right-hand side, you're going to see fingers on a hand. If you can click on that and raise your hand so that I know that you can hear me, that would be great. You are all on mute, so you're not going to be able to talk. I see some hands going up. Thank you. There is a chat section just below on that same panel. If you have any questions, just reach out and I will start answering them. I am going to save the hardest questions for last for Ivan Rakov, as I've done before with Ivan. So please ask away. Now to introduce Ivan. If you don't know Ivan, he's an Apache Ignite contributor. He's one of the core engineers and architects at GridGain. He focuses on a couple areas. We've talked about cluster topology and scaling before. Today, though, Ivan's going to be talking about native persistence and data recovery. So with that, Ivan, let me turn it over to you.
Okay, thank you, Rob. Yeah, my name is Ivan, and today we'll talk how in-memory computing meets database durability. First of all, we'll scan through what in-memory data grids can do and find out that there are some disadvantages. They are not always handy to use, and these disadvantages can be covered by the durability mode. Then we'll take a dive into architecture of Apache Ignite. I participated in development of persistent mode, and I have a hands-on experience, and that's what I'm gonna tell you about. Then we'll move from theory to practice and look through some use cases. I'll tell you how to use durability mode to solve your possible production issues. And then we'll proceed to performance trick section. Durability means working with disk, and disks are usually slow. And I'll tell you how to cook durability mode well in order to minimize negative outcome on performance and your system key characteristics. So let's go. First of all, I think most of you already know it, but what is in-memory data grid? The quick description from my side is it's distributed cache with brains. It allows you to store data in memory, and storing in memory means speed of accessing your data and low latency. And there's not only storing, you can also perform more complex logic, like performing distributed computing in MapReduce style, or working with separate storage, separate database. You can work, you can tune in-memory data grid exactly as a cache, and you will work with your separate database with write-through and read-through mode in order to boost your speed of accessing your data. That's very good, but indeed, do you really need to access all your data at in-memory speed? The point is that perhaps your data can be divided into hot and cold, and most likely you store some cold data, like history of your financial transactions and so on. And most likely you don't need in-memory speed for your cold data. It's reasonable because storing all data in RAM is really expensive. There's a factor of 40 times and server level RAM is 40 times more expensive than server level, production level SSD disks. So if your data can be divided and only part of data requires high speed, maybe it's a point to use durability and to store the cold data on disk. Next point is that sooner or later, any cluster will require maintenance. Indeed, you may want to upgrade your product version or upgrade your hardware or maybe anything else. It doesn't matter. You will need to restore. And if you store your data in memory way, restarting of cluster and killing the process means that all your data will be lost. And of course, you may reload your data again, but it will require some time, and for some time your data will be unavailable. And it would be really handy if you could just restart your cluster and have all of your data. And the last point, but not least, is that anything can happen, and anything that can go wrong will go wrong. And imagine that you reached any kind of disaster in your production. For example, it was an error that you have changed your data scheme in the wrong way or performed some incorrect transaction and your C is ruined. In such case, what people usually do in production environments is data backups. And it would be really handy if you had an option to create and restore data backup in your in-memory data grid environment. And in case you had a backup for some hours ago, you can just restore it and perform something like Ctrl+Z. You can undo your erroneous section and recover state back to normal. Okay, and basically durability mode can achieve all of these points. And first of all, let's take a dive into architecture of Apache Ignite. And in Apache Ignite, there's a durability mode, of course, and it's achieved via transparent page memory architecture. Why page memory and why transparent? There is such abstraction as a page, and every point of data that is stored in your in-memory system is actually stored in page. And page is transparent abstraction, and it can be present or can be not present in RAM, but page in durability mode is always present on disk. And when we change the data and write something to page, let's see what happens. Page becomes dirty and update firstly accumulated only in RAM. It's not synchronously moved to disk. And later, dirty pages accumulate, and when there's enough dirty pages, they are written to disk in batch way, and this is called checkpoint process. Checkpoint is a batch operation, dumping dirty pages to disk. And once checkpoint has happened, your update is already stored on disk. But when we are talking about hot restarts and keeping all your data present in case you need to restart your cluster, there's a question. What will happen to data that wasn't checkpointed yet? The answer is write-ahead log. It's a common abstraction for relational databases. Speaking shortly, all updates are written to write-ahead log first of all, and only after some time they are written in checkpoint. So what will happen if you will restart your node? Part of updates will be recovered because they were written during checkpoint, and that were not written will be recovered from write-ahead log. We will Ignite node reads a write-ahead log for the moment, starting with the moment of last successful checkpoint, and recovers your latest updates. So one way or another, all your updates will be present. This is a simple overview of what happens and how persistence is implemented. Let's proceed to Next point is data backups. And GridGain allows to create data snapshots under load. So all you need to do is execute snapshot create command, and all your data will be written to separate storage in background. You may still operate with your data and change it. Let's see how it happens. Basically, all of your pages are present on disk. What you need to do is just to scan your disk storage and copy all of your pages to separate snapshot storage. But there is a problem because there are conflicting updates. When you say snapshot, you mean snapshot of system for a certain point of time. But next checkpoints, if you change your data, will happen, and they're going to change your pages in your disk storage. So basic scanning doesn't work here because some of pages written during scan will represent snapshot point of time, and some writes will be represent next point of time, which was updated by next checkpoint. So what we can do here is writing. Imagine that next checkpoint comes and it wants to write a page that wasn't written by snapshot scanning yet. In such case, checkpoint process will help snapshot process, and it will perform a cooperative write to snapshot directory. It will write old state of page to snapshot storage, and then overwrite old state of page in disk storage by new state. So at last, all pages, one way or another, will appear in snapshot storage. Okay, let's now move from theory to practice and consider some use cases that are useful and that can be achieved with the data storage configuration and persistent mode. Okay, let's start. Let's start with limiting your RAM consumption of your Ignite node. Why you may want to do it? First of all, that's completely okay to limit your consumption because you may share your cluster, Ignite cluster may share the same hardware as another cluster. For example, you may want to set up a deployment of Ignite and Kafka clusters on the same hardware, and Ignite will do part of the job and Kafka will do another part of the job. Second reason is to not consume all available memory, because in such case, operational system will starve and will not have enough memory for operational system activities. So what you can do in Ignite for such case is to limit overall RAM usage. And there will be a certain limit, and all Ignite caches will operate inside memory region of exactly that size. So what you should do to limit your memory usage is to specify data storage configuration. It's a common entrance point for any configuration activities with your memory and disk storing, and specify a single data region and specify a max size to it. This example shows a max size of 60 gigabytes. Let's see what will happen with your node with such configuration. You have a 60 gigabyte limit for all of your data, and once you load data to your caches, for example, A and B, they will allocate pages in that big chunk of memory by demand, but they certainly won't exceed this 60 gigabyte limit, because once the pages are over in this chunk, there's no another place to allocate new pages, because all pages are separated from this big chunk. Okay, there's an option to perform more precise memory tuning, and you can limit, you can specify different limits for different caches. So in order to achieve that, you may want to specify several data regions and specify a limit for each region. And there's another option. You can configure an eviction mode. Eviction mode is a behavior when if your chunk of memory is overloaded, Ignite node will not crash with something like Ignite out of memory exception. Instead, just all data will be removed. It's really helpful in case you use Ignite exactly as a cache. There's a third-party storage, and there's no problem if your data is removed. You will just load it again from your third party. So here's an example of configuration. There are two data regions, big one and small one. And small one, we have specified eviction mode. Eviction mode means that all data will be automatically removed. So let's see what will happen in such configuration. There's an overload of 60 gigabytes, just like in previous slide, but there are two chunks, 15 and 45 gigabytes, and caches A and B operates in their own chunks. And you can continue loading your data to cache A, but there's no chance that cache A will try to allocate some space that is reserved for cache B. Instead, as it has eviction mode, the data will be just evicted from cache A, and all this data will be found and just removed. So total amount of your data will be still 15 gigabytes, but it will be only the hottest data because coldest data was removed during eviction process. Okay, let's proceed to persistent and what persistent mode is needed for. First of all, is fast restart. So if you configure persistent mode, all pages are present on disk, and there is logic that only part of pages are present in RAM, and the pages are present are hottest, and cold pages are not just removed completely, like in the memory case with eviction mode, they are just replaced to disk. So so basically Ignite node just chooses hottest pages and keeps them in RAM. In order to activate persistence mode, you need to specify data region and set persistence enabled flag as true. In such case, let's see what will happen. For example, two caches, A and B, they both operate in persistent data region. And so when you start loading your data and haven't reached the 60 gigabyte limit yet, all of your data are present in two places. They are present in RAM and present on disk. But when you are getting closer and closer to your limit, when you reach it, part of your data is replaced. So you just find Ignite node just find coldest pages, and they are removed, but removed only from RAM. They are still present on disk, and they are replaced. So in such case, you may continue loading data, and you still gain durability guarantees. You will still keep option of but only hottest part of your pages will be accessible with the high in-memory speed. And the next and most specific use case is when you have hot and cold data. The most common example is when you have operational data set which contains, for example, your current state of your accounts and historical data set as, for example, audit records and or perhaps history of operations. So in such case, if you can divide your memory in hot and cold, you can specify small memory region for your big and cold dataset and large memory region for small and hot dataset. The configuration will look like this. There will be two regions. One is large with persistence enabled, and second for cold data is small and also with the persistence enabled. And let's see how it will work. There are two chunks of memory, 15 gigabyte chunk for cold data and 45 gigabyte chunk for hot. And for example, you know that your data in cache C is cold. It contains history for your transactions. When you continue putting data to cache C, coldest pages will be replaced. And when you load and load data even more, only small amount, on a small percent of your data is present in RAM. That means that if you will access any page, it's most probable scenario that you will require a synchronous read from disk. Yeah, but your hot data, when you still hasn't reached limit, 45 gigabyte limit, is on disk and in RAM. That means that you will still gain durability for all of your caches, A, B, and C. You gain in-memory speed for caches A and B because all pages are present in RAM and you can read them quickly. You don't need to access disk, and you still have all your data from cache C present, but reading is way slower because you need to replace some other. If you need a random page from cache C, you need to replace random page and replace it by the page you need. Very well, let's proceed to next batch of use cases. It's about data snapshots. Data snapshots will help you in case of disaster, but that's not all. There's optimization on GridGain side in case you do snapshots of your non-volatile data on regular basis. Example is the same. Imagine that you have historical data set and a large part of it is not changed from day to day. And if you want to perform daily snapshots, you don't want to copy the same historical data set again and again. We have an optimization for such case. Okay, next point is that sometimes performing local snapshots is not enough, and you may want to need a remote snapshot catalog. And we also have an option for such case. Let's start with disaster protection. In order to back up current state of your system to a separate snapshot folder, all you need to do in GridGain is just to perform snapshot create command, which will execute a background process. And that process will scan your disk storage and copy all of your pages to separate snapshot directory. This is pretty simple. And in case you want to do reverse operation, you can just perform a snapshot restore. Snapshot restore will deactivate your cluster for a moment, and your data will be copied from your separate snapshot storage. And after the separation is finished, all your state of all of your pages is equal to the state for the moment of snapshot creation start. And then you can cluster is activated back and you continue working creation. Okay. And the next case is a regular snapshot of volatile data. And for such case, we have incremental snapshot option. And if you say create an incremental snapshot, only changed pages are written. Changed means changed since last snapshot. So if most part of your historical data set wasn't changed, then those pages will be not written. And in order to achieve that, we pre-calculate information whether or whether or not page was changed in special type of pages. We call them tracking page, and tracking page contain bit masks. And in bit masks, there is 1 if page was changed and 0 is if page wasn't changed. One tracking page cover a range of like 16,000 of regular pages, so it's not really big memory overhead, but when we need to create an incremental snapshot, we already know which pages were modified, and we just scan through the pages that have ones in bit masks. Okay, and what we have discussed is creating local snapshots to some local snapshot storage, and sometimes it may be not enough. First of all, you may bump into a complete disaster when all your local data will be lost, as well as local snapshots. You have a limited disk space, first of all, and if you create snapshots every day, you will run out of space, and that's why you may want to move your all these local snapshots to remote safe network folder and have an option to recover from it later. And the next point why local snapshots are not enough is that your topology may change, and you may want to scale up your cluster or shrink it or replace part of your nodes. And in such case, if you have created a snapshot, for example, 3 months ago, you may just not have all the nodes that were participating in that snapshot. You may have removed them from your cluster. And in such case, you will not be able to restore this snapshot from local files. But if you have already moved that snapshot to network storage, you just execute a command of restore and moved snapshot, and everything will be okay. All your files will be found. So what we can offer in GridGain to achieve such use case is snapshot move command. First of all, you create a snapshot and then execute move command, which moves your all files to network storage and then deletes the snapshot locally. So first of all, that's the state of the system when snapshot create command is executed. So all of your files are present in snapshot directories locally. And then you execute move command and all your files are moved to separate network storage. And of course, you can perform a restore. You can specify a path to your network storage, and this snapshot will be recovered, and local state of your partition files will be replaced by state from remote snapshot. And the point,
Ivan, I'd like to interrupt you for just a moment.
All data partitions will be found. Nodes will just peek in snapshot folders of other nodes. They are not able to find their partitions that they need in their own folders. So all files are in remote folder, and all nodes will have access to partition if at least one node had this partition at the moment of snapshot creation. So you just perform a snapshot restore from remote directory and you don't care about topology changes. Your restore will always succeed. Okay, and even more specific scenario, if you want to restore to some point of time between snapshots. For example, if you create snapshots daily and you want to restore to the middle of the day, there's a point in time recovery option. It's performed, so you just say to this time, and what system does is first of all initial recovery when we perform restore of previous snapshot before that point in time, and then point in time recovery algorithm performs a distributed analysis of write ahead log. It calculates set of transactions that conform to a consistent state. It's kind of distributed algorithm when nodes exchanges what transactions are present locally and overall set of consistent transactions are calculated. Okay. We have covered use cases of how to configure your cluster, how to limit your memory, how to achieve fast restart, and how to protect yourself with data backups. Now let's move to performance tips section. Just a moment. Yeah, let's do performance tip section, and now I'll cover questions how to minimize your performance degradation, because one way or another your system performance will decrease if you are using persistence, because now you need to write to disk, at least you need to write your records to write-ahead log. And the point is that you can configure your production deployments properly and minimize the risk. So just a moment. Oh, okay. I'm sorry, 30 seconds. I think I have opened a previous version of presentation. Just a moment.
And Ivan, if you can hear us, the sound is has been going up and down a little. I think you may have lost your headset.
Yeah, this is correct.
Okay. Okay.
Yeah, let's start with performance tricks. First of all, that you should consider in your production environment is that your memory disk ratio affects performance directly. So every page that is absent in RAM will require synchronous read. So remember, if you remember the picture with hot and cold data sets, only of pages is present in RAM. That means that your latency grows along with the share of disk-only pages. And here's a graph that shows how your operations per second ratio decreases when your memory/disk ratio decreases. So this is a benchmark when we start loading data to grid and we run out of RAM and page replacements to disk starts. And there's a near linear dependency between memory disk ratio and operations per second ratio. That means that if you are planning a production deployment, you also have to estimate your memory disk ratio before going to production. And this will help you to estimate your throughput and latency that your system will be able to handle. Okay, the next case that may suddenly strike you is that if your system will experience peak load throughputs and it can be higher than your disk throughput. If you remember, dirty pages are accumulated in RAM, and when there are lots of dirty pages, checkpoint starts. And if your checkpoint is slower than your dirty pages generating during load, you may experience this kind of pattern. So your operations per second graph is good, but suddenly it drops to 0, and for a significant time, it may be several seconds, then it goes back to normal level, and then again you experience a 0 drop down. And why that happens? So exactly this 0 drop down period is when your checkpoint is not finished yet, but you have already the maximum amount of dirty pages for next checkpoint. So you have already ran out of your RAM. All pages are dirty, but you can't clean them and start next checkpoint because previous checkpoint is not finished yet. So you may happen and you may find yourself in such a situation. There's an option in Ignite to avoid such situation. It's called right throttling. So right throttling is a mode when we estimate approximate speed of checkpoint process, and the Ignite node doesn't allow to make pages dirty and make dirty pages % more than % of pages that is already written to as part of the checkpoint. So in such case, when we are marking pages dirty fast enough, you will experience a drop down, but it will never be a zero drop down. So your operations per second graph will be smoother. It will, of course, will be not smooth as just a horizontal line, but it will never go to zero. And this is helpful, I guess, because in such case you can guarantee that your latency on your operation will be limited. It's, I guess, it's a must option for mission critical deployments when you need low latency. So next moment that you may find yourself in is surprise from SSD drive side. Let's start with details of how SSD operates. First of all, SSD disks are designed to be easily adapted by operational systems. They have a simple interface like write something to that address like hard disk drives, but actually SSD is a complex computer itself. It has its own processor, its own RAM buffer, its own controller, and its own memory. It's actually memory where the data is really stored. But when you say write k bytes to that address, it doesn't mean that there exists an address where this record will be stored. It's way more complex. SSD drives has pages and blocks, and so page is small, for example, 4 kilobytes, and blocks contain a batch of pages, for example, 64. And difference between them is that data is written in page granularity and erased always in block granularity. And the point is that write only an empty page, and if the page is already contains some data, you should erase the whole block in order to make write possible again. And that's like a physical limitation. So erasing page requires applying higher voltage to the block, and it's not possible to apply such voltage to a certain page because this neighboring pages will be affected as well. So they are organized in blocks and isolated better. So if you want to erase a block, you need to shift your useful data to another block in case this block contains some pages that contain useful information. And shifting is surely easy when more free blocks are available. So what does it mean? It means that your SSD performance depends on the percentage of space that is free on your solid state disk drive. So here's a graph when different load patterns were applied to solid state disk drives. So and it showed dependency of write speed in megabytes per second, dependency from percentage of your free space. And you may see that in case pattern is handy, there's only slight decrease in speed when you have reached the limit and you have already used all your free space. But if pattern is not handy, so it's a 100% entropy level, that writes and reads are completely random, and in such case completely full disks operate nearly 3 times worse than nearly completely free disks. So you need to remember this, and to also estimate your percentage of free space in production, and you need, if you run any kind of load testing before going to production, you should handle the same level, you should keep the same level of free space percentage in order to see the same numbers and same results. And the next point is performance issues with solid state disk drives doesn't appear immediately. There's a picture that shows that when SSD disk performance decreases, they happen at instance. So this picture shows when load were applied to several different SSD models, and what is measured is I/O operation, input-output operations per second. And for nearly all models, we see that first of all, IOPS level is good, but then after 30 or more minutes, the load decreases and it slowly goes to some saturation level. So this is the point of drop, is exactly the point when this block shifting from one block to another is no longer able to keep up in background, and it starts to affect operations. So if you perform a load test on your production or pre-production environment with SSDs, you need to ensure that your test is long enough in order to test SSD drives in worst condition. The next performance tip is how to speed up your data load. Your throughput of your system is limited by your disk throughputs with persistent mode, and if you need to load really big amount of your, for example, cold data, it will take a lot of time. So the hint is that every data update is written twice in persistent mode. First of all, it's written to journal or to write ahead log in synchronous way, and it's written to disk storage on checkpoint in asynchronous way. So what we can do is disable write ahead log. Write ahead log is needed for durability, for ability to restart safely. But if your data is not loaded yet, you may not need durability at this point of time. So disable write ahead log. Crash recovery is not guaranteed, but you will gain at least 2 times load throughput boost. So typical pattern is disable write ahead log, load your data, enable write ahead log, and start performing in production way. So you can do it with the following API call. You may call Ignite cluster disable write ahead log plus a cache name, and your loading speed will surely increase. And next point, that how you can improve your throughput of your system in production is using separate devices for separate disk activities. Persistent Ignite node has 4 disk write activities. First of all, it's checkpointing, it's write. There is also write ahead log archive, and it's also activity of transferring all the write ahead log segments to archive directory. And the last one is data snapshotting. When you perform a data snapshot, you also need to write to snapshot folder. And the good news is that you can specify a separate path for each of these activities, literally for each. And if these paths that you have specified relate to different physical devices, each of the activities will work with separate disk drive, and there will be no competition between these activities for a single device. Each of them will work with its own device, and your throughput will be no longer limited by total throughput limit for single disk drive. Okay, and let's. So here's the summary of performance tips. You should plan your memory disk creator before going to production. You should consider using throttling if you have severe latency limitations. you should consider overprovisioning your SSD and keep in mind that amount of free space will affect your performance. For initial data load, you may want to disable write-ahead log to speed it up, and you may consider splitting disk activities on separate storage devices. Okay, I hope that persistent mode with its bonuses and advantages will help you in production. It will help you to make your production less expensive by using hot and cold data pattern, and will help you in maintenance and in disasters by allowing to restart your cluster quickly and protect from disasters by using snapshots. And will be happy and more motivated if you will use our durability mode and provide feedback, and we will add more features in it, and together we can perfect it. So that's it. Thanks for your attention. Now I'm ready to answer your questions.
Okay, great. Ivan, can you hear me?
Yeah, sure.
Okay, perfect. Your voice was going in and out a little bit during the session, so I just want to make sure you can hear me, and if you're close to the mic, that'll help. The first question was, what is a snapshot in Ignite? I guess it didn't come across clearly when you were doing the theory versus the implementation. So what would you call a snapshot in Ignite?
Okay. The question is that in pure Apache Ignite, how you can achieve a snapshot, yeah?
I think that's a good way of answering it, yeah.
Okay, so the answer is that in Ignite itself, without the GridGain plugin, there is no way to perform a hot snapshot. There's no way to perform a snapshot under load, but you still, so if state of your system is determined by state of your disk storage, you can do it in two ways. First of all, you can deactivate your cluster or shut it down, and in such case, no one will write in your disk storage and write-ahead log, and you can just take your disk storage and copy it somewhere else, and this is actually a snapshot. If you need to recover your state for that moment, you just perform a reverse operation. You shut down your cluster and recover your previously saved state. So when you start, your state of the system will exactly be equal to the state for the point of time of first cluster deactivation. There is even no need to shut down your cluster if you are sure that your data will be not changed. So what you can do in another way is to, for example, if you have a cluster in read-only mode, you just want to read your data but not write, and you can snapshot it by just copying your files of your live cluster. You are doing it on your own risk, because if some updates will finally come, you will copy inconsistent state of pages. But if there will be no updates, for sure this will work as a snapshot.
Okay, and when I deactivate the cluster, I'm immediately in state. I can just copy the partitions and the write-ahead log to another disk.
Yes, this is true, because when we deactivate an Ignite cluster, we perform a last checkpoint, and after this last checkpoint is finished, all data is present on disk, and then cluster just gets shut down. So when you access your disk storage after that, it will contain all last updates.
Okay, so now second question. Let's say I do this and then I have to restore. I'll do this in two parts. First, you have to restore to an identical version of the cluster, correct?
Okay, you mean that identical version is the same topology, the same set of nodes, yeah?
Yes.
Okay, the answer is yes and no. if you're performing the snapshot with manual files copying like I have just described in Ignite, your topology should be the same, and the same, nearly the same is for GridGain local snapshots. When you perform a snapshot create, then snapshot restore, you can lose a small part of your nodes in case you have a big backup factor, in case your partitions are present in multiple copies. For example, there are 3 copies, you can lose 2 nodes. But if you want to restore snapshot after significant topology changes, what you can do is exactly perform snapshot move and then restore from shared network directory. So in such case, there are no topology limitations, and doesn't matter on which topology the snapshot was created, it will be recovered anyway. So in any topology.
Okay, and then the second part of the question is, there was a question of what do you mean by momentarily? I think that the question was, how fast does an Ignite cluster recover before it can start handling requests?
Okay. So when Ignite cluster starts, it actually has all the data present, but first of all, it needs to read write-ahead log with latest updates. It's kind of dependent how much data were written to write-ahead log. So I guess it's exactly the same amount that you need to. So imagine size of your updates since last checkpoint in bytes, and imagine the time. Imagine the speed which your SSD drive allows to read the data from your SSD. So this will be exactly the answer. All updates will be read from write-ahead log that were written since last checkpoint, and after that your system will be operating. Your Ignite node will join into topology and will handle requests to read and write data. So if you want numbers like some seconds, so I guess I give you a formula from the checkpoint frequency. So checkpoint frequency is parameter which specifies how fast and how often checkpoints are taken. So in practice, there are something like maximum 10 or 20 seconds, I guess, if you have checkpoint frequency like 3 minutes. If in case you will decrease your checkpoint frequency, start time will also decrease.
This is basically how fast you can rewrite the write-ahead log into memory.
Yeah, exactly.
Yep, got it. Okay.
Yeah, and right after restart, you will experience a small throughput drop down because all your data is called at that time. All your data is present on disk, and every read for the first time will require reloading the page from RAM. But very fast after that, your RAM will be filled with hot pages, and then your system will operate at normal level.
Great, perfect. So you can basically dial down your checkpointing times to dial down your recovery times. That makes good sense.
Yeah, that's true.
So there's this very specific question, how do we recover segmented partitions, which I think means recovering specific partitions and specific nodes if they get corrupted. I'm not sure.
Mm-hmm. Okay, what is segmented partitions? I didn't get it, but in case part of your, imagine that part of your data is corrupted, yeah, and you are not able to recover the state of page. So there are several options. First of all, when we understand that our page is corrupted, we will perform an attempt to restore its state from write-ahead log. So there's kind of The page is present in two places in the write-ahead log if it was written recently and on disk storage. And first of all, we'll try to recover its state from write-ahead log if it's broken on disk. But in case that will not help, node will just shut down, but it's still okay in distributed system, because if you have large cluster and you have backup factor, for example, backup factor of three, losing your node is not a problem, because you just get this node out of topology, you just clean your data and just the node again with clean local disk storage. And then all the data will be rebalanced to the new node again. So right now, corrupted storage mean losing of local data on the nodes, but chance of corruption is not really high. It's really small, and but you can lose data on one node, but it's still distributed system. It still doesn't mean that you have lost your data in distributed system manner.
And there are various checks to see whether data has actually gotten corrupted across multiple copies.
Yeah, sure. There's you can check and you can be sure that your data is not corrupted. And there's a control script utilities. So there's control.sh script. I guess you can find it in documentation. And there's idle verify options. Okay. And idle verify option. And if you pass something like checkcrc arguments, this will force this command to check contents of all pages on disk. And if you have executed idle verify -- checkcrc and the result is successful, that means your data is not corrupted.
Okay. Final question. It's a good one. How would you set up persistence when deploying on Kubernetes?
Oh, okay. To be honest, I'm not really familiar with Kubernetes, but I think Kubernetes is just container management system, and there is no, I guess, something special about persistence in Kubernetes. You anyway have somewhere configuration of your nodes, and in that configuration, you just need to set persistence enabled, like I showed you at the beginning of presentation, and make sure that your containers that your Kubernetes is operating with have an access to persistent storage or to persistent drives. So in such case, you will just achieve persistence. So maybe there are more easy commands for our Kubernetes node. So I'm not familiar with them, and I can tell.
Okay, sure. I'll pass on a quick answer. The local persistent volume capability of Kubernetes went GA in April of this year. It was already getting used by American Airlines. American Airlines, I think, talked about it briefly in an in-memory computing summit session back in, was it November of last year in the US. So, but the short of it is, if you use the Kubernetes persistent volumes, you can set it up. So it is running. People are running persistence inside Kubernetes today. It does seem to work well. The challenge, there's a separate webinar on Kubernetes if you want to learn more about it, because Kubernetes, the other challenge is the only ingress into Kubernetes is usually HTTP or HTTPS. So that's a whole different conversation about how you set up your cluster and your client nodes that would connect to it. But the persistence has been shown to work well with the local persistent volume feature in Kubernetes. So I don't see any other questions, Robbie. Sorry, I don't see any other questions here. So I think we are good. So Ivan, I want to thank you for spending all the time going through this. And
thank you, Rob. Thanks all.
And hopefully